Alright, let's start with the basic connection between optimization and data science. On one side, we have mathematical optimization. That's basically the art and science of figuring out the best possible solution when you have got a set of constraints and objectives. Think about situations like deciding how to allocate resources across projects, how to make a process more efficient, how to cut costs, or how to maximize performance. In short, optimization is about making the most effective choice among all the possible ones you could take. And on the other side, we have got data science. Data science is a discipline that digs into data to pull out patterns, to make predictions, and to support decision making. It uses things like statistical analysis, predictive modeling, and even machine learning techniques to find signals in data. So, instead of guessing, data science helps us anticipate what's likely to happen. That's valuable because optimization often needs reliable parameters or forecasts, and data science gives us exactly that. So, if we put the two together, what do we get? Let's look at this. We get enhanced decision making. For example, with data-driven optimization, we are not just relying on fixed models. We are feeding in actual historical and real-time data. And that allows us to handle uncertainty better, build solutions that are more robust, and adjust strategies when conditions change. And a second aspect is automation. Here, systems can tune themselves, adapt in real time, and even learn as they go. Instead of waiting for someone to intervene, these systems can keep improving their decisions with feedback. And there is complex problem solving. Here you can see some problems are not straightforward and they involve multiple objectives that may even conflict with each other. Optimization methods can handle that by balancing goals, and when we add in machine learning, we can even learn constraints or recognize patterns that help shape the solution space. And that's how scalable solutions are built for very large real world problems. Okay, so what happens when you integrate optimization and data science? You don't just get solutions to the same old problems. You can actually discover new ways of formulating those problems, predict the right parameters in advance, and create systems that improve themselves continuously. That's really where intelligent systems come in. So, to give you a clearer idea, let me point to a couple of key integration concepts. And first, in data-driven optimization, you often see it written as like that. Minimize f of x subject to g of x comma theta less than or equal to 0. And here, theta is a parameter that's learned from data. This is how machine learning results get plugged into optimization problems. Next, we have predictive models are written as like that. What's that? Y hat equals ml of x arrow optimization. That simply means the model predicts an output y hat, and then optimization uses that prediction to make better decisions. In reinforcement learning, the standard form looks like pi star equals argmax of expected sum over t of gamma to the power tr of s sub t a sub t. What that means is the algorithm is trying to find the best policy pi star that maximizes long-term rewards through trial and error. So, let's take this further. When we move to the actual applications, one way to study it is through interactive optimization scenarios. For example, if you look at supply chain networks, the goal is to optimize distribution routes and inventory levels. Okay, and if we switch to investment portfolio here, the idea is balancing risk and return across asset classes. Okay, and here you can see our plot. And In production scheduling, we are looking at maximizing throughput while keeping costs under control. What's common across all these is that they depend heavily on data science inputs, things like historical data, demand forecasting, pattern recognition, parameter estimation, and uncertainty modeling. Without these, the optimization would be blind. Let's continue. Predictive optimization. This is where machine learning models step in to forecast parameters or scenarios, and optimization uses those forecasts. So think about demand forecasting. By predicting future demand, we can adjust inventory levels more effectively. In risk assessment, we predict different risk scenarios and then optimize strategies accordingly. Or in resource allocation, the model predicts resource needs like CPU or memory usage, and optimization ensures the allocation is efficient. And notice that each of these models has an accuracy level. Okay, and the higher the accuracy, the more reliable the optimization decisions will be. So, train model, let's see. And for example, risk assessments here. You can see our risk scenarios and dynamic resource allocation. Let's look at this. Alright, what is next? Reinforcement learning here. Instead of relying on static data or predictions, we let an agent interact with its environments and learn over time. And let's take inventory management as an example. The system tries out different actions like ordering more stock, ordering less, or keeping it steady. Based on the costs of holding stock versus the penalties of stockouts, it adjusts and gradually learns the best policy. And in dynamic pricing, the agent adjusts prices in response to demand or competitor moves and learns which pricing strategies maximize revenue. In production scheduling, it experiments with sequences of jobs on machines and learns to minimize delays while keeping throughput high. The important point here is that reinforcement learning links decisions to long-term rewards, not just immediate gains. So, start learning. Okay, and we can do this for dynamic pricing, production scheduling. And let's continue. Real world applications, let's talk about this. So, we'll start with logistics and supply chains. Companies here deal with a wide set of challenges. For example, how do you route transportation across multiple modes, ships, trucks, rail, in a way that works smoothly? Then there is demand uncertainty, especially with seasonal changes. On top of that, you need to keep inventory balanced across different warehouses, and you can't ignore supplier risks. To handle this, solutions usually combine machine learning and optimization. Machine learning helps forecast demand, while network optimization algorithms design efficient routes. Real-time route optimization means the system adjusts on the fly if there are delays or disruptions. Predictive maintenance scheduling helps avoid breakdowns that can block the flow of goods. And what is the outcome of all this? Companies typically see cost reductions between 15 and 25%, and delivery times improve by 20 to 30%, and inventory optimization gains are in the 10 to 20% range. Beyond the numbers, the integration also means decisions are more data-driven, solutions keep adjusting over time, and they can scale to larger networks. And portfolio management is here. difficulties and different it is, and investors face volatility and uncertainty, correlations between many assets, regulatory requirements, and the need to track risks in real time. To cope, methods like Monte Carlo simulation are used to model a wide range of possible scenarios. Mean variance optimization balances risk and return mathematically. Risk factor models help understand exposure to specific drivers, and automated rebalancing keeps portfolios aligned without constant manual oversight. And the numbers here show improvements too. Returns can rise by around 8 to 15%, risk exposure can be reduced by 12 to 20%, and efficiency, meaning how well the portfolio is maintained, can improve by 25 to 40%. Smart manufacturing is here. This area deals with scheduling complexity, making sure products are built in the right sequence and keeping machines running efficiently. Quality control is another big challenge because predicting defects early can save huge amounts. Companies also need maintenance planning and strategies to control energy costs. The solution include predictive quality analytics, which spots defects before they become expensive. And dynamic scheduling algorithms reorganize jobs as conditions change. Condition-based maintenance keeps machines running only when necessary, and energy demand optimization reduces unnecessary consumption. The outcomes are clear. Efficiency increases by 20 to 35%. For example, defects can be cut by 30 to 50%, and maintenance savings often fall between 15 and 25%. And finally, let's look at healthcare resource optimizations. Hospitals face constant pressure to balance staff scheduling, patient flows, equipment usage, and costs while still keeping quality high. Predictive admission models estimate how many patients are likely to arrive so staffing can be planned better. And optimization helps assign shifts and plan capacity. And pathway optimization designs the flow of patients through treatments more efficiently, and the improvements are quite significant. Patient wait times can be reduced by 25 to 40%, for example, and capacity utilization, which is how effectively hospitals use their resources, goes up by 15 to 30%, and overall cost efficiency improves by 10 to 20%. So, across logistics, finance, manufacturing, and healthcare, the message is the same. Optimization provides the framework, data science fills in the details, and together they drive measurable improvements.